So can everyone see my screen?
Yep.
Awesome. Thank you. So this is EEG Signal Analysis Part 1. So this is kind of an overview of what the previous kind of tutorial sessions were about. We just covered how to, ignoring this part really, that's just, we used pre-existing data, but how to import it into EEG Lab, importing the channel locations, and then running it through a filter and examining it and rejecting any like artifacts you see just by eye, like as it says here. So what we're really going to focus on in this kind of session is actually doing the signal analysis and what ICA is, and just introducing that concept. So for the first section, I just want to go over what extracting a data epoch is. So EEG epoching is a procedure in which specific time windows are extracted from a continuous signal. So this is not really specific to EEG Lab, but I thought it was a good like visual reference. So extracting an epoch, it usually references extracting like a specific trial. So you're going to take this data that was maybe trial 1, and then this data from here to here was trial 2. So those are, that's what epoch really references. And I hope this is a good explanation, because I kind of had a little bit of confusion also, like understanding what that concept of an epoch is. So again, these are just some time windows, and they are time locked with respect to an event. So again, an event is, we kind of went over it last week too, but an event is a visual stimulus. So the patient will be looking at maybe a square on the screen, and that's kind of their cue to press a button, and that's what references an event. So an epoch is that time period of seeing that visual stimulus. So what exactly we're going to be doing in EEG Lab, this is just a breakdown of it. This is the GUI, or the GUI, General User Interface, in EEG Lab. It's really simple to work with, I think, but what you want to do specifically is go to Edit and select Extract Data Epochs, and we'll be looking at, so this tells you like what type of event you want to choose. And if you click this button here, which I'll show in EEG Lab, but you can choose an RT or a square event. So based on the data that we're using that's given with the EEG Lab package, a square event is when they see a square on the screen, and then the RT is actually like pressing a button in response to the visual stimulus. So I'm going to stop sharing the PowerPoint and really quickly. All right. So I'm actually using Citrix with EEG Lab, and like just to see how it works, and it's pretty, it's like almost the same process, nothing really different other than, you know, Citrix can be kind of buggy sometimes. But so we're gonna go down to actually tools, not edit, my bad, to extract epochs. And I kind of glossed over it, but this is assuming that you were there for the previous tutorial. So again, you just go through the process of downloading EEG Lab, loading the M file, or just typing it into the directory, and you should get this GUI, and you can hit File and hit Load Existing Data Set. to kind of get to this point. So I'm going to get back to extracting epochs. So here again, we're going to choose the specific square type event and press OK. And here it just kind of shows you the progress. It's epoching, and it'll ask you if you want to save it as anything. So I'm just going to keep it as continuous EEG data epochs, maybe put in 11/24 and hit OK. So sometimes it takes a while for it to kind of show up here, but the name will change here. As you can see, it says data epochs, and then that ... is like the date that we set. And another part of epoching, and this is kind of, again, related to almost filtering the data. This pop-up will automatically show up when you epoch, and it's about baseline removal. And for this one, we're just going to go with the standard, like removing this range of values. But like depending on your data, you can manipulate it. And so again, just removing baseline, and we can just overwrite the epoch data and keep it here. And that's that process. So let me go back to our PowerPoint. So the next thing that I wanted to cover is event-related potentials, otherwise known as ERPs. So an event-related potential is the measured brain response, and it's the direct result of a specific stimulus. So in this case, we were talking about a visual stimulus in the form of a square being shown on the screen. So the difference actually between like an EEG signal and an event-related potential signal is that EEG signals are typically measured during like resting or sleeping, and they're just a continuous signal. And an event-related potential, again, is like this specific spike, the specific stimulus event, the specific time period that the stimulus was shown. So there is a lot of different methods to plot and visualize these event-related potentials. So here is, again, the EEG Lab GUI, and under plot, we can go to channel ERPs, and looking specifically at the whole, like all of the event-related potentials from all the channels. So that would be showing it with the scalp maps here. So again, you can like visualize the channel locations and the kind of average of all these ERP signals. I'm going to stop sharing again. And if at any point you can't see what I'm talking about, please let me know. But so we are going to channel ERPs and with scalp maps. And this pop-up is just, again, what time range you want it, what the title should be, and these can be changed, but we're just going to keep the default values. So it takes a while to load here, but these are the specific locations, and this is the ERP signal. So these are all of the event-related potentials. So it's kind of hard to get like you can't see a single event-related potential associated with a single channel in this type of plot, but it's a good reference because you can kind of scroll along different latencies and you'll see this change. So I just clicked like around here, or actually negative like 121, and you can see the difference of where the potential is acting. And if I click here, then you'll see, maybe click on the spike here. That's kind of a zoomed in version, but let's see. Yeah, so around 86 milliseconds. This is what the activity looks like. I'm going to close this. But there are other methods to visualize event-related potentials. So let's look at that. Now, if we wanted to look at the specific traces on a topographic array, we can choose the second option under channel ERPs, which is in-scalp/rectangular array. So if I choose just the default option in EEG Lab, it will arrange the event-related potentials in this sort of imitating how these channels are placed on the scalp. So that is like this array here, but I can show in EEG Lab what that looks like. And there is also another method. Just the GUI. So back to plot and channel ERPs. So these are all the channels, and you can choose whether to plot the single trials or rectangular array. But for now, again, just using the default values. So this is, again, like that figure where you can see it in how it's placed on the scalp. And if I click on a specific channel, it'll give me a zoomed in version of the event-related potential. So again, Citrix is kind of icky and I can't really move this, but this is that. Click here. We can move on. Yeah, let's move on to the next form of plotting. So you can also plot a series of 2D event-related potentials. So kind of like we were seeing the activity before with the scalp figure, you can see just how those channels act in this demonstration by going to ERP map series and clicking in 2D. So again, here under plot, ERP map series in 2D. And again, we usually don't really need to change the default values. Let me see. I'm gonna let this run for a bit. I think Citrix is lagging on me, but let me stop sharing. Are there any questions about anything? Okay.
Making sense for me.
Awesome. I'm just hoping I'm not going too fast. All right, so I'm going to actually keep going, but I'll share my Citrix screen again. We just need to fill in the latencies. It usually automatically fills it in for you, that's why. But if we go here in 2D, so these need to be filled in, but I might be like getting the format wrong here. Okay, that's good. This is the, again, the ERP in 2D form. So there's those two figures. So what we've been doing so far has been plotting the latencies or the time against the potential, and that's kind of visualizing different ERP signals or from different channels. But there's also another method of visualizing an event-related potential, which is an ERP image. So this plotting mechanism, like based on this text here, is just you change the color value to indicate the potential value at each time point in the trial. And you can stack these lines above each other, and it's kind of a color sequence for all the trials in the data set. So we go here under plot and channel ERP image. That's where you want to go. And you can choose a specific channel. So in this data set, and I'll show later in the GUI as well, where you are given 32 channels. So you have an option between 1 to 32 channels, and you can visualize actually the channel locations, and based on that, pick like a specific channel that you want to enter here to visualize with an ERP image. So this is with POZ or channel 27. And this is what the ERP image will look like. So I'm gonna stop sharing real quick. I need to bring up the GUI again. And here under plot, channel ERP image. So this is the interface that pops up, and let's pick again channel 27. And this smoothing factor, which I will mention later, we can just use a smoothing of 1 now to kind of get the same image as on PowerPoint. So this is kind of that image. And again, here you can see the top is, there's this red dot. It's kind of hard to see, I guess, if I don't know if I'll be able to show you in full screen, but there's a red dot that indicates where this channel is. And down here is just the potential that's like unstacked, or the average. And again, it's against time, and these are the number of trials here. This is kind of hard to look at, or you can't really get a clear idea of what's going on with just this image. So what's recommended is that you can increase the smoothing factor. So if we increase it by 10, you'll be able to kind of find the specific potentials, or where high potentials are going on in the data, or low potentials, for example. So I'm going to real quick show that. Again, plot. ERP image. And instead of 1, let's use a factor of 10. So this smoothed image, again, you can kind of get an idea of at what time point was the high activity going on. And before, it was much harder to visualize that. So again, this is what the image we saw in MATLAB with the higher smoothing factor. Okay, so that is all the information that we need before we can go into independent component analysis. So this is, again, the actual signal analysis part. And this will be just a brief introduction, not really going into the details, but I hope that I can kind of give a good explanation of what really ICA, or independent component analysis, is. So it's a method of recovering a version of the original sources of a signal. So I'm going to use this image here to kind of help explain what that really means. And so if this was like, imagine we were at a party, right? And there are all these microphones, and these are what are picking up specific signals. But instead of like brain signals or EEG signals, what we're talking about here is just audio. So it's going to be picking up this, someone conversing here, this conversation at a dining table, maybe a band playing. And what ICA does is it takes this information from all these microphones and it breaks it down to each component. So you can hear specifically then what the violinist is playing, what this person is talking about, what the trombone player is playing, and what here this person is talking about. So in terms of EEG or EEG lab, what that means is the microphones are the electrodes that are placed on the scalp. So we have all these electrodes placed, but what's happening is that in the cortex, we're going to get a signal from here and a specific signal from here, depending on whatever stimulus it is, right? So these signals are going to be picked up by all the electrodes at some level. So this electrode will get the most of maybe this signal, but then by these like kind of waves, you can see that this electrode is also, or these two electrodes are picking up this signal, but then this signal is also being sent from this electrode to this electrode to all of these electrodes. And that's really difficult to measure. So let's go to ICA Formula. And this formula is, it's really simple, I think, but it's like we don't have to know the specific like statistical analysis and details behind it. So just a kind of explanation of what it is it is the data is multiplied by this unmixing matrix so that you can get the specific components. So X is like the pure EEG signal data or the ERP data, and it's represented by the channels against time. And your output is the ICA components. So that's components versus time. And W is the ICA unmixing matrix that you want to multiply by the data, and that's components by channels. So again, just a visual kind of explanation of what that is these scalp channels pick up some linear mixture of A and B. So again, it's a linear equation, U equals WX. We're assuming that these are combined in a linear mixture. And these are the brain sources here, A and B. And so some form of it is picked up by scalp channel 1, and brain source B again gives some value to scalp channel 2 or scalp channel 1, and the same thing for scalp channel 2. And we can maybe say that the length of these arrows is kind of how much of brain source B is in scalp channel 1 and brain source A is in scalp channel 1. So what ICA is doing is taking this curve here and these two and running an analysis so that you can head back to the specific sources. And again, another sort of visual demonstration. These are maybe the channels that we're working with in EEG lab. And once we apply this unmixing matrix W, we're going to get the independent components IC1, IC2, IC3, IC4. And ICA in MATLAB is actually really simple. All you have to do is go to tools and hit decompose data by ICA. And you can visualize it by plotting the component maps. So this section about components is usually unavailable to you until you've run ICA. And also another note, you want to run the ICA analysis once you've epoch'd the data. So you need to extract epochs and run through that process before you get to decomposing the data. And this is the graph that you actually get. So I actually visualized all of the channels, all the independent components, but you can, since it's a lot of different things to look at, you can visualize maybe like 1 through 6 and then so on and so forth. So I'm going to head to MATLAB. So I have actually run ICA to another data set already because it takes a while. So there's that note. If you're planning on running the ICA, just make sure that you don't have to interrupt it at any point because it will take a bit to calculate. So this is the epoch data that has also, the ICA has also been run on it. And maybe we can, yeah, so this component options are available, and I just hit component maps in 2D. Instead of 32 components, maybe let's do again 6 instead, and hit OK. So I think it's pretty cool how you can kind of see it get plotted and then see the color map show up. But yeah, those are the specific components. And there's other ways to visualize it and actually other ways to keep going with the analysis. But again, I'm just doing the basics right now. Oh, and do we have a question? Sorry, I'm having some troubles. Oh, no worries. All right. So the last section of this presentation is how to do data averaging in EEG lab. So to compare these event-related EEG dynamics. You can select for 2 or more conditions and then compare or average them or find the standard deviation, etc. So what you actually want to do is just create the data set containing a specific epoch for each condition.
I'm gonna see if the
So I will keep going with that. So again, it's under edit and select epochs. This is where you're selecting for a specific epoch, and the actual analysis that you want to do is under plot and then sum and compare ERPs. So this is the result that you will get. Depending on your settings, mine are under like 1 through 32 as the channels are, or as the components are. And you can click on a specific component to see the comparison of the data. And so that was the square event type at position 1, square event type at position 2, what the average looks like, and what's the standard deviation. So I will quickly demonstrate that in MATLAB. So I also have the square position 1 data set ready to go, but under plot, or not plot yet, first we need 2 types of epochs or events to compare. So I'm going to select epoch or event. And here under stimulus position, I have the position 1 data computed already. So I'm going to just select stimulus position 2 and hit keep only selected events and remove all other events and remove epochs not referenced by any selected event. So hit OK, and it'll give you this warning, but that's all right. You can, you want to delete the unreferenced ones, keep going. And the next part will be saving the data set. So I'm just going to save it kind of like the presentation, square position 2, hit OK. And now under data sets, you'll have this one. So I've already done square position 1, but and what you want to do is that since EEG Lab automatically opens this square position 2, and if you're going to make, like, for example, if this was the first time I was doing it and I made square position 1, I wouldn't go right to edit and select epochs or events because you're still under square position 1. You need to click data sets and go back to your continuous EEG data. So yeah. Now what we can do is go to sum and compare ERPs. And the data sets to average, let me double check that. So this is number 6. So you want to keep note of the numbers. And data set 3. So I will just put in 3, 6, and I want to see the average, the standard deviation, and all of the event related potentials, and hit, oh, before you do that, select for a significance level. So 0.05 is kind of a standard significant level, and hit OK. It's running here. Again, making all these traces. And kind of like the ERP plots, you can, once this is done computing, you can select a specific component that you want to look at. So let's look at one. It looks the busiest. Let's see if it's going to load today. Okay. So this is, again, square position 1. Ooh, lots of graphs. Let's just click on one. Figure, square position 1, So we're position 2, the comparison, the average, and the standard deviation. Yeah. And I think that was the last part of the presentation, yeah.